Hello, everybody. Today, we will discuss a very little bit about galactic structures and we'll build up this on the last two lectures or the prerequisites and the last lecture. Now, when I say galactic structure, first let us define what is a galaxy. Galaxy is a large collection of stars. How large? Well, at least it will have like 10 to the 6, 10 to the 7 stars. A typical galaxy will have about say 10 to the 10 stars, 10 to the 9, 10 to the 10 stars. It can be more, it can be less, but this is a ballpark number. It's not only stars which makes the galaxy, it also has gas, mostly H1, and other stuff, all in between the stars. So we call these as interstellar medium. And it is believed today that the entire galaxy resides in a dark matter halo. Now that's roughly a galaxy, what a galaxy is. But then it turns out that depending on the shape or the morphology of the galaxy, you can divide a galaxy into mostly three parts. One is disk or spiral galaxy. Elliptical galaxies. And then you have lenticular or irregular galaxies. Disk or spiral galaxies, we'll see a picture shortly and we'll discuss mostly about a disk or spiral galaxy. It's basically, it is first order, it's a disk, and in the second order, you see spiral structures in the disk. Elliptical galaxies are more like ellipsoids, and so elliptical galaxies has less interstellar medium. It is believed that they are older galaxies, and irregular galaxies does not have much regular shape. That's why they are called irregular. And so it may be that these galaxies are colliding and make an irregular galaxy. There are a lot of things which we'll not be able to talk about in one lecture, obviously, but let us see how much we can do about the galaxies. Now, we will mostly talk about spiral galaxies, but before we do that, let us look at a little bit about the two pictures, one of elliptical, one of spiral. So this is an elliptical galaxy. The point-like objects that you see in the foreground are the stars from our galaxy, so they are not important for this picture. The fuzzy thing that you see in the middle, which is more like a structure with a lot of stars, and you cannot make out the individual stars. That is why you call it is looking like this. So that's an elliptical galaxy. That's how an elliptical galaxy will look in optical wavelengths. The color here has nothing to do with the color we see. This is called a false color image. It's just that one particular intensity is given, one intensity in that color. This is a picture of a spiral galaxy and disk galaxy. Immediately you see that it is not like mostly, it doesn't have that nice spherical type of appearance. By the way, there are a lot of stars from our galaxy in front of the galaxy. Ignore them. All the point-like objects are stars. Ignore them. But in the center, what you see like a disk kind of object is the external spiral galaxy we're talking about. And you see that, first of all, it's a disk. There is way of knowing what is the three-dimensional structure of it. It's known that this type of galaxies are disks. And then you see these nice spiral arms coming around, going around the galaxy. You see, also notice that spiral arms fades out at the outer part. The spiral arms actually cease to exist beyond a certain radius. There are, if you count, maybe 4 spiral arms here, very prominent, and they also starts from a certain inner radius. Inside, there is not much evidence of a spiral arm. Having shown you the picture of two types of galaxies, let us come back to the uh, spiral galaxy now. So directly we'll dive into spiral galaxies. We will not talk about anything else from now on. Well, let me talk a little bit about still of a type of galaxy sometimes are called dwarf galaxies, which are basically galaxies of smaller size. Nothing more into that. Okay. So spiral galaxies, as we said, it has stars and gas. The ellipticals does not have much of gas. And I'm keeping it in bracket, it also resides in dark matter halo. And I will just give you a very, very brief, abridged version of how do we know that they resides in a dark matter halo, or how do we come to that conclusion. So this galaxy, so let's take one example, our galaxy itself. And as I said, that it's a disk. So the disk has some thickness and some radius. So I say this is the radius and this is the thickness, right? Obviously, for a real galaxy, it is a little more complicated structure, but 0th order, it's a disk like this. It's also that this disk is not stable. I mean, it can be stable, sorry, but this disk is not steady, it's rotating. So there is a rotation of the disk. Now, when I think of a disk, a real disk is a rigid body. So a rigid body or rigid disk rotates. This you must have studied in your classical mechanics course, says that the angular velocity, we call it capital omega here, is same everywhere in the disk. Right? So that is a famous theorem in classical mechanics. Actually, if there is a rigid body which is rotating about some point or some axis, then the angular velocity about that axis at all points in the rigid body is a constant number. Galaxies don't rotate like a rigid body. Now, what do I mean when I say that galaxies rotate? I mean that the stars in the galaxy and the gas in the galaxy, they rotate. Well, obviously, that is what makes the galaxy. So when I say galaxies rotate, I should mean that they rotate. So the galaxies do not rotate like rigid bodies, which means that omega is not a constant. Omega is a function of r. Okay. Now that is quite explainable because you see, if I look at a galaxy, if I now try to look at the galaxy, so let me give you some terminologies. If I look the galaxy from a side, it's called the edge on view. So the edge on view of this galaxy will be more like a flat thing. On the other hand, if you look it from the top, you will see the entire circle. It will look like circular, like the galaxies I showed you. It's as a circular view. It's called a face-on view. Okay. And depending on how the disk of the galaxy, it's a 2D disk, right? So how it is oriented in the sky, your face and edge, and it can have face on view or can have edge on view. Now, for a typical galaxy, the radius of the galaxy, let's call that RG, and this HG. RG is about, now I have to ask the question that what is the radius that I'm talking about? Now, if it is of stars, it is about 10 kiloparsec. Again, these are ballpark numbers. If I talk about H1, then it can be quite larger. It can be, say, 25, 30 kiloparsec, even larger sometimes. Okay. So the gas is extended much more outwards in a disk. So that is important for us right now. We'll see how. Now, in one of the prerequisite lectures, you have seen that you can measure the velocity of the gas, H1 gas, in different parts of the galaxy. So if I measure the velocity that we measure can be the tangential rotation velocity. So if it is rotating, so I can define a tangential rotation velocity, and we know how that it will be related to this. So the V tangential rotation velocity is r cross omega, so r omega essentially. So I can measure that as a function of radius, and I can plot that as a function of radius. And this is how it is known that omega is different at different radius, because Vt is what we can measure, but we can infer omega out of it. For a typical galaxy, it will rise initially, and you see what do you expect to happen after the initial rise. Why it is rising initially? So this is about, say, 10 kiloparsec. It is rising initially because as you go outwards, you include more stars. So the mass that is pulling a star, so if I imagine there is a star here, the mass that is pulling that stars towards the center, if you use Gauss's law, is the mass inside that dashed circle. As I go outwards, so if there is a star here, the mass that is pulling the star is certainly more. So because of that, it need to have more rotational velocity such that it can balance that gravitational force. So it's a centrifugal force balancing the gravitational pull. But then when you come here, remember that the gas extends beyond the stellar disk. So what I have plotted here, if it is a stellar disk, so the gas disk will be somewhere here. And then if I look at the gas here, that's also rotating. And just by the method we discussed earlier, we can find out the tangential rotation velocity. Now the gas weighs 1/10 of the stars. So for all practical purposes, there I don't need to include the mass of the gas. So the stars don't increase anymore. But as I go outside, the gravitational pull decreases. It reduces, as you know, with 1 by r square. So I'll require less rotational velocity to support that gravitational pull. So that's what you expected, that it will go down. But when you observe, you see that it almost remains constant. To the far, you can observe. So this is called rotation curve, and this is called the flatness of the rotation curve. And one explanation for this is that there is another type of matter which we call the dark matter, within quotes here or within brackets here, and that is what is there even outside the stellar and the H1 radius, and that against that pull, the pull of the dark matter, the gas or the star has to balance itself. because of that it maintains a higher rotational velocity. This was first observed by Vera Rubin and later it was hypothesized that the dark matter is the culprit for having this. Okay, so having said that, so this is important because this tells you also that the stars and the gas are rotating in almost circular orbits. So that question is important, that they're rotating in almost circular orbits. Okay. Now let us discuss that a model of rotation in almost circular orbit. So we have looked at the effective potential in one of the lectures earlier. So if I have a star in the galaxy, any star in the galaxy, I'm talking about stars here, it will apply to H1 gas also. See a potential. So in a mean potential, in all cases, it should be a gravitational potential, but I just don't write the gravitational part, created by all other stars gas, etc., dark matter, etc. Right? And then we came out with the idea of the effective potential. Remember, we said that the V effective as a function of R, which gives you an equivalent one-dimensional picture in the central force problem. Let me draw that for you here. So this is the radius R. Maybe I should use capital R here because that's what I have used a little while back. And the potential, remember, this depends on the actual gravitational potential that there is and the specific angular momentum. Actual gravitational potential need not be 1 by r square. That will depend on the density distribution, right? So this may look something like this. I'm just drawing something, but it has a minima. Okay, and say the minima is at r equals to 0, or not, r equals to r0. So what is the orbit that I expect about r equals to r0? So about r equals r0, we will get circular orbit, right? So here I will get circular orbit. So this is where the V effective is minimum. Now let us say that we will look at, just like in the previous case, we said that the stars are kind of moving in almost circular orbits. So let us say that if it is moving in almost circular orbits, then the potential that the stars see must be very near to V effective minimum. So if that for that the energy of the star has to be here, and that will corresponds to one R minimum and one R maximum, right? And remember that the star can never go outside R minimum and the region R bracketed by R minimum and R maximum. It will always stay in that annulus region. So what we will do is we will write V effective as if we are seeing as seen from R equals to R naught, which essentially means that we are expanding it in terms of R naught. So let's see what happens. So V effective will be, there will be V effective minimum, that is the value there at R equals to R naught. Then I have del V effective del R at R naught times R minus R naught. We'll write one more term, del 2 V effective del R2 evaluated at R naught of R minus R naught square and higher orders. Okay, now you see that the first term doesn't matter. This is irrelevant because we are doing classical mechanics. Absolute value of the potential is not important. The second term, V effective del R is essentially 0 at V effective equals to V effective equals V effective minimum, because that is the definition of a minimum. So this is 0. So here you see that V effective as seen, so I am writing here R naught. So this means that with respect to R naught is half of something which is, let's call this kappa, and then R minus R naught. Square. Let's call this kappa square. What is kappa square? Kappa square is del 2 V effective del R2 at R naught. And if you write down V effective in terms of V and L, this will have a del 2 V del R2 at R naught, this term, and then you will have 3L square. This you can check from the previous discussions. And if you work out a little bit, del 2 V del R2 at R naught, you can write in terms of omega, which is the omega at R naught. So the angular velocity here is omega. So I can write kappa square as R del omega square del R plus 4 omega square. Everything obviously evaluated at R naught. Okay, if you need a complete thing, omega is L by R square. This is just definition of omega, or definition of L, so to say. Now, all right, so we have done some mathematics. What we have done, so we said that I will look at this star, essentially, the star which is moving in this orbit from this point. So I will go to that point at R equals to R naught. I will move with the angular velocity omega with the star at R naught and look at the stars which are moving at with E star energy. Okay, so let's see what will I see. So let me draw this orbit with the radius r0. Okay, and say I am sitting on this orbit and moving with the angular velocity omega at r0. What will I see? The star at not r0 but which is having that E star energy, what will that do? That will go around this point essentially. Why? How do I know that it will go around? Well, its radius, the change in the radius will oscillate about this point. That we know because here you see I get a V effective for that star as seeing from here, and that V effective is a harmonic oscillator potential, right? So sitting from here, and this is called the guiding center. I will see that the radius of the other star oscillates about this point and it's also rotating. If you think of a little bit and work out, you will see that it will do a circular motion. The angular frequency, so there are two things happening here. One is that the orbits at r0 gives the guiding center. Which moves with an angular speed omega, right? And then there is an oscillation about the guiding center of angular frequency. What will be the angular frequency of this oscillation? Well, we know already that it should be k, kappa, because just looking at the potential, we can tell that. So this has an angular frequency of kappa. Now you see what will happen. Let's say the case where kappa is equals to, so let's say kappa is equals to omega. So by the time, so let's try to draw this kappa equals to omega curve here. So this is the guiding center circle, and say at when the star was here, the value of the distance r minus r0 is 0. So what will happen as the time progresses? The distance will increase, not to very large value, remember. It has to come to 0 in 2 pi because they have the same frequency, and then the distance will decrease and then it will come back here. So roughly speaking, this orbit will be a circle, right? It will be almost a circular orbit. What if I have kappa equals 2 omega? Let's try to do that. So it starts from here. Kappa is 2 times, so it completes the rotation 2 times by the time 1 omega rotation is completed. So if I just draw this, so in this part it is outside, this part it is inside, and then again it is outside, and then again it is inside. So you can see visually this makes an ellipse, right? In general, if I need a closed orbit, kappa has to be some number times omega. Okay, so this method of looking at the orbit has a name. It's called the guiding center approximation. Obviously, it's an approximation. Remember that in the V effective, we neglected the higher order terms. We'll need this idea shortly. Fine. So having come up to this, let us discuss about the spiral structures in the spiral galaxies. So you've seen the orbits of the individual stars, but how do they make a nice spiral structure? Initially, there was a theory which tried to explain the spiral structure, and the theory goes in the following way. It said that, say this is my galactic disk. So it said for some reason there was a bar kind of overdensity formed. So this is at t equals to 0, overdensity of stars at some time t equals to 0. At the time when it is formed, I call it t equals to 0. Now, as time progresses, what will happen? You see, there is differential rotation. So the end which is O and the end which is A will rotate at different speeds, different angular speeds. Differential rotation means that they will rotate at different angular speeds. So with time, different parts of it would have rotated by different amount. So the theory tells that differential rotation creates spiral structure. Okay. Now the spiral structure can be this way. The rotation can also, can be this way also. It depends on how it is how the disk is rotating and all. So what I'm drawing here with this dash shaded region is the overdensity of stars. That's what a spiral structure is by any means. It's the overdensity of stars. Okay. Now it turns out that this theory doesn't work. This is a very good example because you come up with a theory and then try to apply it, and then you see that it doesn't fit the observational data. You have to discard the theory. So why it doesn't work? So let me explain to you. So for that, so I have to draw the spiral structure once more, and I have to define something called the pitch angle. So if I consider a star here, so this is the radius vector to the star. This is the angle by which the position of the star. So I can draw a tangent to the spiral at this place. This is the tangent to the spiral, and I can draw a line which is perpendicular to the radial line, right? So the angle between these two are called the pitch angle. So let's call this I. So this is tangent and this is drawn by keeping this 90 degree. Okay. So this is the pitch angle. Now I will not go through the calculation because it will take some time, but you can see that cotangent of the pitch angle in this case will be given by r del phi del r. This is just by the definition of the pitch angle. This will be true without any approximation, just from the definition of the pitch angle. Okay. Now, in this model, how is the spiral structure created? Because of differential rotation, right? So if I ask you that what is the value of phi of a given point after a certain time r, certain time t, what is the value of phi at a given r, so phi means this phi, which is obviously I am talking of the spiral arm, a star in the spiral arm. So I the location of that star I can give by r and phi. I'm asking after time t, from when this bar is formed, what will be the value of that phi? So it will be phi, depend on r and t both obviously, equals wherever the bar was initially, let's say that is 0, and then what is the angular velocity at that radius times t, right? This is as simple as that, phi equals to omega times t. So then I can calculate del phi del r, that is just del omega del r times t. So I can calculate now cot I for this assumption. So this is a general formula. This is coming from this assumption, how the spiral arm is created. This will be r times t times modulus of del omega del r. Now what you can do is that we can look at a particular spiral arm and see what will happen. As you keep on going, this end will keep on rotating and this end will not rotate at all. So this end will stay there and this will keep on rotating. So it will keep on winded up. So the spiral arm after some time will look something like that, right? So if I fix a certain phi in this is my phi, the it goes through the arms at different points, right? So if I call this, say, the point A, this, say, the point B, so I can write phi A at the radius RA is omega at RA times T, phi B at the radius RB is omega at RB times T. And if these two are just the adjacent spiral arms, then you will agree that phi B is 2 pi plus phi A. It has rotated 2 pi times once more, 2 pi times extra. So you can calculate this angular, this radial difference between the two spiral arms. So the two spiral arms, in that case, I can ask the question, how much apart these two spiral arms will be? So how do I calculate that? So let's go through the calculation once. So I have 2 pi equals phi b minus phi a, which is omega r plus delta r. So Ra plus delta Ra minus omega Ra times T. And if you work it out, you will see, so this I can do a Taylor series expansion. First term will cancel out, delta Ra will cancel out, omega at Ra will cancel out. The second term will have del omega del r, which I can replace by cot I from here. So what I will get by doing all this is delta r as 2 pi r by cot I. Okay. Now, let's say what was observed. Observationally, we have seen so many spiral arms in so many spiral galaxies. So observationally, it is found that the delta r, which is the distance between two spiral arms, is at least 1 kiloparsec, sometimes more. And I is more like 5-10 degrees. Okay, even more sometimes. If you do the calculations here, so let me give you some numbers for a galaxy. I told you that R is for the largest radius is 10 kiloparsec for the stars. Vt, the tangential rotation velocity at the flattening point, is about 200 km per second. This is where the rotation curve is here. If you put these numbers, this will give you an I of around 0.25 degree and delta R around 0.3 parsec, which is much, both of them are much less than what is observed. So these values are. So this particular theory, how the spiral structures are generated, does not work. Okay, so having said that, now we will discuss the theory which explain the spiral structure quite well. This theory is called the density wave theory. In the previous theory, we saw that a word density is developed, and then the overdensity, as because of differential rotation, goes at different positions. So the stars which is there in this overdensity always stays in that spiral arms. Stars do not go out of the spiral arms, right? So this type of arms are called material arms. So which are created by specific materials. The materials never goes out of the arm. Materials are stars, of course. In the density wave theory, it is said that it's not a material arm, it's rather an arm created by density waves. Means that just like a wave, the density, so if it's a sound wave, the density variation propagates. Similarly, for the spiral arms, there is this density variation which will propagate, which will make the spiral arms. At different times, the spiral arms will be made up by different stars, not the same stars always. Okay. Now, to see the density wave theory, first we have to look at a galaxy and go to the guiding center approximation. So let me draw the effective potential again here. Maybe something looks like this. Should go to 0 at infinity. I assume that it is happening. And the minima is here. And we look at the orbits of the star with respect to the guiding center. Okay. So we go to, maybe we do not go to the exact reference frame of this. So we go to a reference frame. We'll see why we bring in that. We go to a reference frame. And that from an observer outside, it has an angular velocity omega p. P here stands for pattern. We'll see why it is important. So from that frame, angular velocity of the stars is omega. If I call it omega prime, it's omega minus omega p. Omega is the actual angular velocity of the star. So this omega is a function of r, of course. It is different at different radius. And I have go to a certain reference frame which is rotating with a certain angular velocity omega p. So I see all the stars around me rotating with omega, actual angular velocity of the star, minus omega p angular velocity. Now, which omega p I go to, I can choose that. If we choose omega p equals omega minus kappa by 2. So for that particular star, it sees a potential. That potential has a omega, which is the omega here. That's the rotational velocity of the star around the galaxy. And then it has a kappa, which is the epicyclic frequency, the frequency in which it oscillates in that guiding, around that guiding center. If I choose omega p to be omega minus kappa by 2, then what happens? This implies that omega prime is omega minus omega plus kappa by 2. So this is just kappa by 2. What is the advantage then? Remember that if omega is kappa by 2, let's see what happened when we choose omega is kappa by 2. So when omega is kappa by 2, we saw that the orbit became ellipse. So which essentially means now, looking from this reference frame where the angular velocity is omega p, I will see the stars moving in an ellipse. So in this reference frame, right? But wait a second, there is a catch. The catch is this omega and kappa are function of r. Stars at different radius has different values of omega and kappa because they see different effective potential. So this has to be true. The fact that I go to a omega p, what am I doing? I am just going to a rotating reference frame. Maybe I am sitting in a cart which is rotating with respect to the galaxy at a angular velocity as omega p, and looking at the pattern, the stellar structures in the galaxy, right? Now it turns out that I can make an ellipse. I will see that every star is moving in an ellipse if omega p I choose to be omega minus kappa by 2. But that value of omega p depends on a certain radius. In all radius, omega minus kappa by 2 will not be the same. It turns out though, there is a range of radius where omega p, or which is omega, or which is not, which is equals omega minus kappa by 2, this remains constant. So that is nice for me, because then for all the stars in all those radius, they will appear to move like ellipses for me. Okay, and this will be important for us. So let's see what we have done and then we'll proceed. So we first go to a rotating reference frame. We choose a reference frame such that the orbits look like ellipses. But then we realize that I can do only for a certain radius where the effective potential is such that I can choose omega p to be omega minus kappa by 2 and it will look like ellipses. But then for every galaxy there is a range of radius where the omega minus kappa by 2 doesn't change. So if I go to that particular reference frame, then all these radiuses will look like an ellipse over a certain range of radius. So now this is the first part of the puzzle. So this is one, and then these are the sub parts of the puzzle. We are making up a new theory of spiral structure. This fortunately works. Second part is we build up the spiral structures out of elliptical stellar orbits. Basically, we arrange the orbits. Okay, so how do I arrange the orbits? So let me show you how we can arrange the orbits. Here in this picture, there are many ellipses, and two ellipses I have shown in black. But you see at the center, the ellipse is like the major axis is around the x-axis, and then what has happened as the radius or the semi-major axis of the ellipse has increased is that perihelion of each ellipse has rotated a little bit, corresponds to the previous one. And that's how I have drawn so many ellipses. Actually, I think there are 32 of them. If you look at it carefully, what has happened by arranging the ellipse this way is that there is a crowding of the orbits along where you see more blue color. That is just an artifact of how I have arranged it. And interestingly, the blue colors kind of make out a spiral pattern. So it is just, if I arrange the ellipses this way, it is supposed to make up such spiral pattern. This is another example where the ellipticity is less, but you can see very nice spiral patterns in and out. And as I said, beyond a certain radius, it will not be effective. So I have not drawn beyond a certain radius. So that is how you make the ellipses. That is how you make the spiral structures. But then the question is, it's all right, you make such a structure, will this structure be stable? So the next question is, somehow maybe the structures came up, but will the structure be stable? And that is the last thing that we'll discuss today. And we will see that this analysis is quite complicated, and I will not do the entire analysis. I will just tell you how to do it. And then at the end, I will even not discuss the stability of the spiral structures. I will just discuss the stability of a differentially rotating disk. But the formulation that we will do can also discuss the stability of spiral structure. Just that I will not be able to do the analysis in maybe another 10 minutes that I have. Okay. So how does it work? How do I look at the stability? First of all, we take an assumption. It's a 2D system. Says that I took coordinates as we have been using r and phi. So the other direction, thickness is assumed to be 0. Okay. So now I can write the surface density is essentially mass per unit area. The density is mass per unit volume, but because we have 2D disk, it's mass per unit area. And let's call that capital sigma. It will be a function of r and phi. And we are asking whether this structure is stable, so which essentially the surface density is stable. So I should start by writing it as a function of t as well. Now this we assume as an unperturbed part, a part which never changes with time, and it only depends on r. So this is unperturbed. And then I have the perturbed part, which depends on all three. Okay. So this is the density. The velocity v is a vector, is a function of r phi and t, and it has the tangential rotation velocity, which is only a function of r. I'm sorry, it's not r cap, obviously, it's phi cap. And then it will also have its perturbation, which I write as delta v, which can be function of r phi and p. Okay, so this is just the harmonic analysis that we did last time. With this, we exactly do the same harmonic analysis. Now there are different things. We are working in 2 dimensions. Second, our unperturbed and perturbed parts looks different. Third, we have a non-zero velocity here for the unperturbed part. So these are both unperturbed, up and down. And fourth, we have uh, in the back of the mind a certain type of structure, which like the spiral structures. Now, when I say spiral structures, there is a certain number of arms which you can have. We cannot say I have 3.5 spiral arms. That doesn't make much sense, right? So what you do is you start by writing this down, the perturbed parts, the fluctuations, start by doing harmonic decompositions of them. And because the harmonic terms arises only because of phi, the r is changing in the perturbed part also. So you do the harmonic decomposition in a particular way. And finally, you obviously use the continuity and the Euler equation. So you sum it over m modes, and you have an amplitude and a phase. Just like before, it looks a little different here. Usually, when we write such things, we would have written m phi plus kr, but here, because this is also a function of r, it is not so simple. Second thing is, this m belongs to integer only, because phi is a periodic variable, not like goes from minus infinity to plus infinity, but goes from 0 to 2 pi and repeat itself. So we'll get only integer numbers here if I decompose it this way. And you can define a radial wave number k, which is del f del r. Okay, so I will not go through any further calculation now that I have defined all the quantities that we'll need for the next discussion. Let me tell you still that what will you do with this? Well, we have done this harmonic decomposition of one term here, but we can also do the harmonic decomposition of delta v in the same way, and then put that into our continuity in Euler equation now for 2 dimensions, and to do the entire harmonic analysis, we'll finally get the dispersion relation. So let me write down directly the dispersion relation here. Okay, so when you write the dispersion relation, so K has come out to be this, but F, once I expand with respect to time, will also has omega t times of kind of term. Omega is the frequency of that oscillation. These things we have discussed. So this is not the full harmonic decomposition. So I have also have to do it in time. So it is only done in radius. We can discuss these things more in the discussion session if you really want to know. But in the bottom line, we come up with a dispersion relation which looks like this. And every term we have already discussed, so I will not need to write down them here. Sigma 0, remember, can be a function of r. So this relation is written for different r's separately. Va square is the sound speed or the velocity dispersion, just like we had before. Okay, now this looks a lot more complicated than the simple dispersion relation we had for the Jeans instability. So first thing is m will give you the number of spiral arms. So m gives the numbers of spiral arms. And as I said, we'll just look at the dispersion relation for a disk. For simplicity, we will choose m equals to 0. So if you analyze this dispersion relation, you can get for any spiral arm. One thing I forgot to mention, which is very important, is that we assume here in the analysis that only local density gives rise to the gravity, or local over density gives rise to the local excess gravity, which will drive the perturbation in or out of equilibrium. So this was done by Lin and Xu. So this is called Lin-Xu hypothesis. This works quite well. So if I'm looking at one part of the arm, I just need to look at or need to count the density at at that location. So once you choose m equals to 0, this simplifies a lot. So this becomes now more like our old relation. Omega square equals kappa square minus 2 pi g sigma naught modulus of k Va square k square. The right hand side is a function of k, so let me call this fk. And remember that stability means omega square greater than 0. If we need to have a stable disk, all modes should be such that all modes should be stable, right? So all the modes should be stable if I want to have a stable disk. Now see, fk is the equation of a parabola. A parabola can be either this way or can be this way, right? If I plot x-axis k and y-axis fk. At k tends to plus or minus infinity, stable, if it is a stable disk, Fk must be greater than 0 because Fk is omega square, so should be greater than 0 at k tends to plus infinity or minus infinity if all modes are stable. This implies that the Fk, so this will happen when the Fk minimum is greater than 0, because if Fk minimum is greater than 0, then everything will be greater than 0. So it's the case here of the parabola. First of all, if all modes are stable, you cannot have the inverted parabola because then k plus minus infinity, obviously Fk will be negative. And if all modes are stable, then I have to have this type of parabola, but I cannot have a parabola which is part of which is lesser than 0, but then omega square will be less than 0, there it will not be stable. So better I have it here, the minima at minima greater than 0. Now, where is the minima? Is equals to 0. If you work this out, you will see that the k at minima will be pi g sigma naught by Vs square. And if I put that back in Fk and calculate Fk at minima, this will be minus pi square g square epsilon naught square. Please do these calculations, we just don't have time to go through them. Then kappa square. And remember, for stability, what is the condition? That Fk minima should be greater than 0, greater than or equals to. So the criteria for stability criteria can be written as Vs kappa by pi g sigma naught greater than 1. This thing is often called Q, so it should be Q greater than 1. Q is called the Tumre parameter. And this stability criteria is called the Tumre stability criteria. Q is often also named as Tumre Q. But you see, just looking at the dispersion relation, maybe the calculation is complicated, you do not go through it. The lecture became too longer, etc. But still, we get back the stability criteria for a rotating disk from looking at this. Now, this is a disk which doesn't have any spiral arm because n equals to 0. This is a disk which is stable for all k's. That is how you got the stability criteria. If you have m not equals to 0, if you work with this full dispersion relation, then for different m, what you will find is that the disk, or the not a disk shape now, the shape will be that of a spiral arm, but that will be stable in between a certain radius to a certain radius. And those radiuses, so between these two radiuses, you will see the spiral arms. Inside you will not see, outside you will not see. So that comes out from the analysis of the dispersion relation, which unfortunately we don't have time to go through. So those two are called the Lindbergh resonances, the inner and the outer Lindbergh resonances. So if I have to draw it, so you will see that there is these radiuses in between which the spiral structures are stable. And this region becomes narrower as you have more and more spiral arms, as m increases. And because of that, you don't see very large number of spiral arms in any galaxy. The reason that there is a inner and outer radius, you can also understand, is because of the fact, remember that for this density wave theory to work, we have to go to a rotating reference frame where omega p has to be omega minus kappa by 2. That will be valid mostly within this radius. And the last thing I wanted to tell you is that now you know, looking from this rotating reference frame, you will see that the spiral structure is stable. If I go back to the reference frame of the galaxy, or the center of the galaxy, or some observer outside the galaxy, then you will see that this spiral structure is rotating with an angular velocity of omega p. That's why the p came in there. It's called this pattern speed of the spiral pattern. I think that's it for the spiral structure of the galaxy. I can give you references from where you can learn it in a lot detail. What I have told you today comes from 3 chapters uh, in a galactic structure and dynamics book, and you can imagine that I have packed in a lot of things from different places. I'll give you a reference to look at them together. I'm sorry that this lecture became really long. Thank you.